So this is the introduction of our DWDM tutorial. We will start from the very beginning. So in early days, networks were actually scattered, and people were doing networks or designing networks or designing different kind of communication channels. But the problem they faced that nobody was following any specific format or protocol or framework or structure. Everybody was trying to come up with their own, right? So I'm talking about very early days, right? So in the 1970s, in that time window, so International Organization for Standardization, they try to come forward with an idea or with a framework that people should have a common structure of communication so that interoperability is possible. They should have a defined protocols or defined layers so that people can actually connect with each other and one another, right? So that's the very conceptual fundamentals of OSI layer. And later in 1977, ISO began to draft a model. And in late 1977, ITU also started working on the same kind of concept. And later, around 1984, both the concepts from both the ITU and International Organization of Standardization, they are merged into one framework, which is called Open System Interconnect or Open System Interconnection uh, layers. So OSI layers in short, right? So this is the very beginning of things getting structured in a very specific way. So in OSI layer, what happened, we got indication or we got a specific set of protocols working in specific layers so that when people are working with different types of networks, they know at which layer they're working and they know how to do the handshake with the other layer, right? So all the protocols, all the communication structure has been structured by this OSI layer. So if we talk details about OSI layer, we know there are 7 layers in the OSI layer. So physical layer, data link layer, network layer, transport layer, session layer, presentation layer, application layer, right? So in short, you will see that this is the diagram for OSI layer, where for the physical layer, it's only about the bits. For the data link layer, it's about the frames. For the network layer, it's about the packets. For the transport layer, it's about the segments. And for all the other layers, it's about the data only, right? Because for the session presentation application, these layers actually being used from host to host. So it's all about data. And for all the other layers, they are the very primary or basics of or building blocks of extending communication from one point to another. So in the physical layer, we talk about all the physical media, all the raw signals, or all the binary inputs and outputs, 0 and 1, right? So this is all about physical layers. That is why we work with bits in the physical layer. For the data link layer, we work with the physical address like MAC address, media access, control access, etc. So whenever we work with the data link layer, we work with the frame because in layer 2, there is no concept of packet. There is a concept of frame, right? And when we go to the next layer, which is network layer, we start working with different protocols, different protocols like routing protocols or Ethernets, right? We start working with IP addresses, right? So this layer is now working with different kind of packets from one point to another. There is a source, there's a destination, and all those things come into the network layer. And after that, we have the transport layer. So transport layer is end-to-end connection and reliability. So this is basically the protocols involving TCP or UDP or something like that, right? So whenever we are working with TCP, there is there is a connection-oriented protocol. Whenever we work with UDP, this is not a connection-oriented protocol. So in this layer, we get error-free communication. We Because TCP makes sure that the uh, receiver has received the packet from the sender. Otherwise, TCP retransmission works, right? So this is the transport layer is all about. That is why it works with segment, right? And then all the other layers, session, presentation, application, they are basically trying to make sure that the user is being able to interact with the service, and the user can actually access the service with a visual interaction from human side. So these are the layers which work with the user data. So this is all, they all together construct the OSI layers, and starting from the physical layer up to application layer, if you follow the whole stream, you will be able to explain how a network works, right? If you take a look at the network, you will find that there are PC or host or end user or terminals where the communication starts, right? So from there, so there are cables, there are optical fibers, then it goes to hubs, then it goes to switches, then it goes to routers. The packets are marked by the routing protocols and decided where to go from where. It looks into the source and destination and all those other parameters, and then it forwards the packet to the next hop. And this is how a packet travels, starting from the terminal at the user and going through the whole network from one router to another, right? One by one. So if you take a look, and if you take a look closely, you will see that all the layers we have just discussed in OSI layer are being used here, right? So what is a network? So network is basically composed of several nodes, and these nodes are basically switching nodes. They switch packets, they switch all the communication units from one node to another, right? And they basically help to build a whole layer of communication segment which can carry user data from one point to another, right? This is a very simplistic way of explaining what is network, right? And if you want to understand how the nodes are switching the data or packets from one point to another, you need to understand the way it works, this switching. So you can basically describe a network into two categories. It can be a packet switching network, it can be a circuit switching network. So when we talk about packet switching network, we basically talk about IP domain, we basically talk about routing domain, we basically talk about Ethernets. So it's all about packets, right? Packets being transported from one point to another. from one node to another. And there is no fixed path for all the packets. So if you take a look at the diagram, there are several routers, and you can see there are two paths from R1, right? So one packet might go to one path, and another packet might go to another path based on the routing policy, based on the source, or based on the destination, whatever works in the domain. So there is no fixed path for packet. The packet can take any path based on the routing protocol. So this is the basic highlight for packet switching.
Oh, Zubia, sorry to disturb.
Yeah.
Are you sharing your screen?
Okay, I might forget. Yes, I was not sharing. I'm really sorry, guys. I didn't notice. Thanks, Kendrick, for.
No worries. Just a couple of housekeeping rule. I realized there's a participant who has a same account name under Suhil. Could you please verify if, because I've seen on the list that there's a lot of people using your name. Are you there, Suhil?
um, Sohail Thakur. Are you talking to Sohail Thakur, Kendrick?
So Suhil Khan. Suhil Khan.
It is Suhail M. Khan.
Okay. Yeah.
Zubia, do you want to continue?
Yeah, I want to continue. Yeah. Thank you, Kendrick. So I'm going to share the screen. Yeah. Yeah. Okay. So as I was discussing about the packet switching network, as I was saying that there is no fixed path for packet switching network, there is no specific route. The packet might take any path, any route based on the protocol, based on the source or destination. And then we have circuit switching networks. So circuit switching networks are networks which have specific declared dedicated paths from one point to another for all the data, for all the communication channels to travel with. So here, actually, you need to set up the path before the communication starts, and this path remains fixed and it does not dynamically change. It does not have that flexibility, and that path is dedicatedly used for that circuit. And in this way, you make sure that all the data over one specific circuit stays on the specific path from the very beginning till the end of the communication. So this is the major difference between these two kinds of network, packet switching and circuit switching. So when we talk about circuit switching, we talk about transparent dedicated communication channel. When we talk about packet switching, we talk about flexible IP packets, which can take any path based on the decision of the routing protocol, right? So we are going to discuss DWDM, and if we ask if anybody want to volunteer to answer or want to engage with, can anybody tell me in which layer of OSI you can place DWDM? Anybody?
Physical.
Physics, layer one.
Yeah. Hi.
Anybody?
Uh,
Anybody?
yes. This is transport layer.
Transport layer. Wow, interesting. So, what do you think it is? It could be transport layer. Why?
So it is transporting uh, bulk of traffic. It transports bulk traffic from X to Y.
True. Does the transportation of traffic from X to Y. But if you take a look at the transport layer of OSI layer, it is in the fourth layer. So before reaching the transport layer, you have to accomplish layer one,
Physical layer. Right.
layer two,
Yeah.
layer
Morning.
layer three, IP. So do you think DWDM has IP in its traffic?
That is only on payload side.
No, that is only on payload side, but within the DWDM,
Hello.
it,
Good morning. My voice is clear. My audio.
uh, please raise your hand before start talking so that it doesn't create any kind of chaos. So currently I'm talking with could you please say your name?
Yeah, Amresh Kumar Pathak.
Okay, I was talking to Shekhar first. So Amresh, let me complete the discussion with Shekhar and then I will come back to you, Amresh. Is that okay?
Okay. Thank you so much. Yes, start now. Carry on, sir.
Thank you. Yes,
It's layer one. It's layer one within which the DWDM operates.
exactly, it's layer one because in DWDM, it's transporting all the traffic as in verb. So the transport here is working as a verb, right? It's not the protocol we are talking about. When we talk about OSI layers, you have to go all the layers up to reach the transport. So you have to do the physical layer, you have to do the data layer, you have to do the IP layer, then you are there at the transport layer. So in transport layer, there is TCP and UDP. So in DWDM, neither of the protocol works for the technology. For DWDM, it's only dedicated channel. It's all about optics. It's all about fiber, right? So that is why DWDM falls into layer one. It doesn't fall into layer four. Is that clear?
Yeah.
I didn't see the name who was talking to me and who said it is in transport layer.
Hey, hi. So Karthik this side.
Karthik. Oh, Karthik.
Yeah. So I got your point, and point is well taken and understood. Thank you
thank
for the.
thank you very much.
My,
Yes, Rich.
yeah, good morning. My one query is these are is CCNA classes, then this is for DWDM classes.
This is for DWDM classes.
Okay, so maximum visit at that mixing that CCNA, like that OSI model
It
you explain OSI
no,
model.
yes, there will be a
Okay.
couple of things which will be discussed to make you guys understand where it is coming from. So because of explaining the OSI model, now you understand where DWDM works. It works in layer one. Is that clear, Amrish?
Yes, sir. Clear, clear.
Thank you. Thank you very much. So, so does anybody has any other query? Please raise your hand. If not, I will move forward. So as I was discussing, there is a circuit switching network, packet switching network. So DWDM is kind of fall into the circuit switching network, right? It doesn't work with packets. It basically work in layer one, right? So in layer one means it has dedicated channel based on light, based on fiber. So since we are talking about traffic and we are talking about fiber, so if we take a look at the trends of global traffic increasing day by day, we are seeing a huge increment of global traffic in past couple of years. So if you take a look, that you will see around 2022, the global mobile broadband traffic reached to 913 exabyte, right? And for fixed broadband, it went to 4,378 exabyte, right? And if you calculate the percentage, around 30% increment. And this increment happened within 2019 to 2022. That means 19, 20, 21, 22. So 4 years, within 4 years. So within 4 years, we can see 30% increment of global IP traffic. On the other hand, if you take a look on the market of optical fiber, only 6.9% is increased by 2030. And this calculation is done based on the last couple of years calculation, right? So we are talking about 2030, that is 6 years from now. They are anticipating that only 6.9% annual growth will be there for optical fiber after 6 years from now. And if we take a look back in 2022, for last 4 years, there were 30% rise in IP traffic. So you can see that there is a huge gap in between the requirement of optical fibers and availability of optical fibers, right? So the amount of traffic we're getting day by day, we are facing day by day is very, very big to handle all over the world with fibers only. So what is the solution? So what is the way out? The solution or the way out is basically doing multiplexing. So what is multiplexing? Multiplexing means using one fiber and use that fiber to carry multiple signals of data so that multiple sources of data can use one single fiber, right? So multiple signals are multiplexed into one single signal, and that signal is transmitted through one fiber. This is how lots of traffic can be accumulated, or lots of traffic can be aggregated into one single fiber. That is how we can actually manage the rise of the global IP traffic within our limited optical fiber resources, because expanding optical fiber network is very, very costly, right? And it is also very much time consuming, right? So we have to make sure that we are using each and every available optical fiber resource to the fullest if we can. And doing multiplexing is one of the key concept of achieving that. So if we go back to our early days or basics, there are a couple of multiplexing techniques like space division multiplexing, frequency division multiplexing, code division multiplexing, time division multiplexing, and wave division multiplexing. So in space division multiplexing, what happens from source to destination? All these signals are transmitted in their separate space, in their dedicated space. So if there are four channels at the source, four sources and four destinations, they all talk to each other with their own dedicated channel, right? So which is basically using one single fiber for one communication, right? This is the general concept of phase division multiplexing. Then we come to the idea of frequency division multiplexing, where all the data are transmitted at different frequency over one single channel or one physical channel or one optical fiber, right? So here what is happening, multiple sources, multiple destinations, but they are connected with one single fiber and they are sending their data in different frequencies at the same time throughout the same optical fiber. So this is how the data are segregated at the destination based on the frequency it is being transmitted. So this is how multiple sources are using the same physical resource, same optical fiber, right? Then we have code division multiplexing. So in code division multiplexing, what happens, all the data from different sources are coded in different codes or different algorithms. At the receiving end, those those codes are being decoded, and then the data is achieved by the destination. They are also using the same physical optical fiber, same single channel to transmit all the data at the same time. So it just having multiple people talking at the same time in the same room in different languages. So only one language is known to you, and you will be understand the language of that person. You will not be able to understand the language of different persons because their languages are different. So in code division multiplexing, the codes are different for different sources. So one destination can understand its corresponding source only because they have the matching code within them. Then we have time division multiplexing. Here, data is transmitted from source to destination over one physical optical fiber single channel with different time slots or with different time windows. So this is how the data is being transmitted. So if there are 4 users in the source or 4 sources and 4 destinations, so the data of source 1 and then 2, then C, then B, then source 4, they will send their data one after another in their own time division, in their own time segment. And at the destination, data will reach the destination based on that time division or time segment. And last but not the least, wave division multiplexing, WDM. So what is wave division multiplexing? Wave division multiplexing is something where all the data are sent in different wavelengths, right? So what happens? So what do we know about wavelengths? Wavelengths means the distance of 2 peaks of 2 consecutive waves, right? So if we have a sine wave and a repeat sine wave one after another, so the peak difference between 2 peaks, the difference between 2 peaks, that distance is called the wavelength of that wave, right? So in wave division multiplexing technique, we send data over one single optical fiber or one single channel in different wavelengths. So at the destination, the corresponding wavelength reaches the corresponding destination, and thus data is extracted from that wavelength. This is how it works. So when we talk about multiplexing, the opposite phenomena or the opposite end working activities we called demultiplexing. So in multiplexing, what are we doing? We are trying to send a number of data from different number of sources over one single fiber within one signal, right? But at the destination end, we will try to do the reverse process. We will try to break that one signal and try to uh, try to achieve all the data for different destinations, right? So this is what we call demultiplexing. So multiplexing, demultiplexing, these are the two ideas of blend. So as you can see in the diagram, at the small user A, B, C, D end, they are doing the multiplexing, and at the capital user A, B, C, D end, they are doing the demultiplexing, right? So it's like using a highway, and there are separate lanes, and different cars are running over their respective lanes, and at the end of the street they are going through the same bridge one after another. So all the ideas are basically very much similar to the transportation system. If you like to compare, if you like to make it simpler, or come up with simple analogy, it actually is similar to the transportation system we have in our real life. So these are the multiplexing techniques we talk about, and we are going to discuss wavelength division multiplexing in a more detailed way in our coming slides to explain what DWDM is. For now, this is the end of our introduction. So I'd like to have questions from the attendees. So please raise your hand if you have any question in this slide, or if you want to discuss anything in this slide. Yes, Amitav, your mic is mute. Yeah.
Yes, sir. I'm just question one thing, sir. FDM only applicable for analog signal, or it can be applicable for digital signal also?
So frequency division multiplexing you're talking about?
Yes, sir. Yes.
So all these communication multiplexing techniques, they are basically analog. So whenever we are working with lights, it is physical layer, right? So whenever we are doing this kind of multiplexing, we are sending all the uh, data over light, right? This is physical media. So whenever we are working with physical media, basically we are working with analogs, right? So yeah, it will be analog.
Okay, sir.
Thank you,
Thank you.
Amitabh. If anyone has any query. Yes, Eddie.
Uh, yeah, my query is regarding the critical difference between frequency division multiplexing and wavelength division multiplexing.
Okay. So the difference between wavelength and frequency is that first you need to understand the difference between wavelength and frequency. So what is wavelength? What is frequency? So the frequency is that the definition of frequency is what is the cycle, what is the rate a wave transmit a complete cycle, right? So if it is a sine wave, so what is the time it took to complete the cycle and then regenerate, right? That is the definition of frequency. And if you understand the definition of wavelength, it is the difference between one peak to another peak, and the difference in the length between these two peak is what we call wavelength, right? So the difference between these two is hidden in its definition. So when we talk about frequency division multiplexing, we are basically working with the frequency of the wave, uh, the data we are transmitting from source to destination. We are talking about the frequency of the wave. For wavelength division multiplexing, we are working with the wavelengths of the wave, not the frequency. So for wavelengths, it might have a lower frequency, it might have a higher frequency, but we're focusing on the wavelength, right? For the frequency, it might have a higher wavelength, it might have a lower wavelength, doesn't matter. We are working with that specific frequency, how fast the cycle is being completed for the wave, and how fast it is doing the starting the second cycle. So this is the definition of frequency. So if we talk about the communication method is the same, one end multiplexing, another end demultiplexing. passing through the same fiber, passing through one signal, one specific signal, and then at the receiver end, it is being segregated based on the frequency it was sent by the source, right? So maybe if you take a look at the picture, you can see we have the definition. We have the example picture of space division multiplexing and time division multiplexing. If we talk about frequency division multiplexing, in that case, user A, B, C, and D would send all the data all together at the same time, but their frequency will be different. That means they are throwing different uh, segment of data, and those segmentations are based on their own frequency. So maybe user A has a frequency, user B has a frequency, user C has a different frequency, and user D has a different frequency. And they all send or transmit the data at the same time through the same optical fiber. And at the receiver end, the capital user A, capital user B, capital user C, capital user D will receive the data based on the frequency which was sent, because the small user A and the capital user A are working with the same frequency, which is different from B, which is different from C, which is different from D, right? So they are different with each other, but they're similar with their own, right? So small a, capital A, they have the same frequency. When small a send the data with frequency, it reaches user capital A with the same frequency, and it can then read the data. So this is how the frequency division multiplexing works. For wave division multiplexing, it's about the wavelength. So what happens? User A, user B, user C, user D, they have different wavelengths of data. Maybe one of them is sending, just for example, maybe one of them is sending red, one of them is sending yellow, one of them is sending green, one of them is sending blue. Maybe at the receiver end, they will be treated based on the color. So they will be treated based on the color. And as we know, the color is different. The color becomes different based on the wavelength, right? So this is the main difference between FDM and WDM, if that answers your question.
Yes, yes. Thank you.
So anybody has anything else? No. So in that case, I will move forward with the next topic, which is the physics of light propagation, right? So we are going to have a break after 5 minutes, and we will have a break for 30 minutes, and then we will restart or resume our second session. So now I'm going to start the discussion on the physics of light propagation. Yes, Rais. Your mic is mute, Rais. I cannot hear you.
I sir, I want to know the more efficient will be frequency division multiplexing or this wavelength division multiplexing.
Definitely wavelength division multiplexing. Why? I will let you know in upcoming slides, but for now, you just take the answer. It will be WDM.
Thank you.
Okay, thank you, Rais, for bringing that up. So as I was saying, DWDM works in layer 1 and it basically is all about lights. So before starting the discussion on
Good morning, sir. हाँ sir.
Who please raise your hand first. Guys, you can lower your hand.
हाँ sir. चल जाएगा.
Who is this?
चल जाएगा sir.
Okay, moving forward. So, as I was saying, that since DWDM is all about lights and all about layer one. So before understanding the technology, we need to understand how light behave. So what is the basic on which DWDM works, right? So what kind of light we are talking about? So that we need to know. So in this session, we are going to discuss all the properties of light which are necessary or which are required to know for understanding the basic technology of DWDM. So I think it's 2:42. Before starting this, we should take the break, and we will come after 30 minutes, and then we will resume the session. I'm going to start a timer here for everybody. Okay, yeah. So I'm going to put that here. And I'm going to share the screen. I hope you guys are seeing the timer, right?
Yes.
Okay. So let's hit the timer zip, then we'll start our second session. Welcome back, everybody. So we would like to resume the session after the break. Thanks for taking the early break with me. So I was craving for a cup of coffee. Okay, so is it's still being recorded? Yeah, it is.
इससे नहीं जुड़ पा रही है यार हमारे लैपटॉप से काहे नहीं जुड़ पा रही है बस यही दिक्कत है
Asking everybody to mute their mic.
हैंग भी कर गया साला हम्म,
So I was talking about the physics of light propagation, right? So as I said in the first segment that DWDM is basically all about lights and fibers. So we need to understand how light behaves, how light is used in this technology to carry data from one place to another. How is it even possible to carry such a large chunk of data from one place to another using only light? So before going into the overview or working principle of DWDM, let's try to understand how light behaves, right? So as you can see, light is used to transmit data in optical communication system. It is true for DWDM, it is true for CWDM, it is true for any kind of WDM. So whenever we're working with communication, optical communication, we're basically using light to complete the communication. And for any kind of WDM technology, it might be CWDM or DWDM, we are basically using different wavelengths of the light from one place to another to carry data. And we are using those wavelengths as a separate channel within the same fiber. So light has two interesting phenomena. One is called reflection, another one is called refraction. But before reaching this phenomena, we need to understand what is light. Light is basically an electromagnetic wave, right? So it has a electric part, it has a magnetic part, and altogether it is an electromagnetic wave. So it moves in two axes, two planes. One plane is for magnetic field, another plane is for electric field. So when it moves in two planes simultaneously, and each plane represents a specific function of light, right? So light works as a particle and light works as a wave as well. So when we refer light as a wave, we basically mean it is an electromagnetic wave. That means it has two axes or two planes to travel. One plane is for electric part, another plane is for magnetic part, right? So as we were discussing, light has two interesting features. One of them is called reflection, another one is called refraction. This is early day physics, guys, very early day physics. So reflection, what is reflection? When light bounces back after hitting a surface, that phenomena is called reflection. So if we place if we place light, or if we put light on a shining surface, it reflects back to us, or it reflects back to some other direction, right? Based on the direction you are throwing the light, right? So this is reflection. And what is refraction? So refraction is the phenomena which shows that when light changes medium, so when light enters from one medium to another, maybe water to air or air to water, it changes direction. It changes direction a little bit in angle, right? So before explaining refraction, there are some terms you need to understand. First term is angle of incidence. So what is angle of incidence? The angle between the light beam and a normal to the surface or a perpendicular line to the surface. So as you can see here in this diagram, there are two surfaces or there are two medium. One is air, another one is water. And in between these two medium, if you draw a line straight perpendicular between these two medium, when you throw the light or when you put the light from one medium to another, in this diagram, you are throwing light from water to air, right? So these two mediums have two different kind of density, right? One is light density medium, which is air. Another one is a very thick density medium, which is water. So when you throw a light from water to air, as you can see, light doesn't go straight in the line. It changes direction a little bit towards the denser medium, that is little bit towards water. So the angle you are throwing the light in the water medium, that angle is called angle of incidence, and that angle is calculated in between the light beam and the perpendicular normal line in between these two layers, as you can see, right? Here, theta 1 or theta I actually, right? This one, right? So this is the angle of incidence. And this is the angle of refraction. So here, as you can see, the light bends a little bit towards the denser medium. So when this refraction becomes 90-degree with the perpendicular line between these two medium, and for the angle of incidence for which this phenomena happens, we call this angle of incidence as critical angle, right? So critical angle is the angle between the light beam and the perpendicular line for which the refracted line goes 90-degree angle with the perpendicular line. As you can see in this diagram, here the refractive or refraction or refracted ray or refracted line is at 90-degree with this angle, with this perpendicular line, right? And this angle of incidence is called critical angle of incidence, right? Critical angle. And if light is thrown at a greater angle than critical angle, then this refracted light comes back into the same media. It doesn't go into the other media, right? This phenomena is called total internal reflection. So this total internal reflection is used in optical communication to carry on optical signal in the optical fiber glass core. So what happens in optical fiber? There is core, there is cladding. The core has a denser medium than the cladding, so the light is injected in such a way so that the total internal reflection occurs, and in this way, light moves forward in a zigzag manner, right? We will discuss about this process in later slides, but for now, just try to understand that light has few features. Among those features, reflection and refraction are two important features. And in refraction, we also know about a unique situation where the light comes back into the same media rather than going forward into the different media. And this phenomena is called total internal reflection. It only happens if the angle of incident is greater than the critical angle. So what is critical angle? Critical angle is the angle of incident for which the refracted ray will be at 90-degree angle with the perpendicular line between two media, right? So these are the basic fundamentals of light. These are the basic working mechanism with the help of which light move forward in optical fiber. And based on this, we use optical communication channel entirely based on these basic fundamentals of light physics. So wavelengths and color spectrum. So there are visible ray, there are invisible ray. So there are some segment of light which we do not see. There are some segment of light which we see. We can differentiate between different colors, right? There are different colors. Those colors we are seeing, they fall into the visible range of optical wavelength range. And there are two extreme points. One extreme point is ultraviolet ray, and another extreme point is infrared ray. So whenever we talk about optical communication in DWDM, we are basically talking about the infrared zone. So DWDM basically works in the infrared zone, right? Not in the visible light zone, okay? As I was saying, how light moves forward within a fiber core. So as you can see, this is a lateral segmentation or lateral bisection of fiber. So there are core, glass core, there are cladding. So light is sent through the fiber and it falls into the core of the fiber, optical fiber, in such a way that the angle of incident is larger than the critical angle, and thus light completely refracted inside the glass core only, and then the refracted ray falls into the other side of the glass core in such a way that again total internal reflection occurs. So in this way, by repeated occurring of total internal reflection, light moves forward in a zigzag way. So this is how basically light moves into an optical fiber, right? This is the basic concept. When we transmit light within optical fiber, there are few more phenomena which we face because of the physics of light. These phenomena are called attenuation, dispersion, polarization, and nonlinearity. We will try to discuss all these phenomena one by one. So these features are important because when we work with DWDM, we face all these phenomena as well. Because as I was saying in the beginning, DWDM is nothing but the game of light and fiber. So whatever light has, it will be shown or it will be there in the DWDM technology as well. And gradually, you will see in DWDM, we use more concepts of the physics of light in this technology. I will share those slides in my upcoming slides as well. So just bear with me. So what is attenuation and what is dispersion? So attenuation is basically the weakening of signal over time and distance. So as time goes by and as distance is crossed by by light in a medium, the signal becomes weak because of the attenuation factor of the medium and because of the decay of the energy of light. So this is the phenomena which we call attenuation. So the attenuation is basically dependent on the material of the medium in which light is traveling through. So the medium basically defines what will be the attenuation of light in the process of traveling from one point to another through that medium, right? And dispersion is basically spreading of the wave over distance and time. So as you can see in the diagram, at first both the lines were in the same shape, the blue and the dotted orange. And as time goes by, the blue line is the expected line which it was supposed to be followed, but the orange line is the practical line which it has become over spending time and distance. And this phenomena is called a dispersion, where the wave is spreading and it overlaps with the another one. So this is how the dispersion occurs. Next, we have polarization of light. So what is polarization of light? So as we discussed in the beginning, light is an electromagnetic wave, right? It has two planes, right? It has electric plane, it has magnetic plane. So whenever we are talking about normal light, like sun rays or open light without any kind of filter or any kind of obstruction or control mechanism, we are talking about open energy. We are talking about electric field being perpendicular to the direction of light in different angles, in different positions, in different directions, right? So in communication or in communication channels, we need to have a fixed direction light from source to destination. So to do that, we need to make sure that the electric field is aligned with the magnetic field, and both of them are destined towards the same direction from source to destination. This phenomena is called polarization of light. As you can see in the diagram, the polarization of light. So in this phenomena, there are few terms. One of the terms is called unpolarized light, where the fields are not being controlled or maintained in any way. That means the electric field is independently working along with the magnetic field and there is no control mechanism, right? There is polarized light, which means a filter has been placed and it is made sure that both the waves, electric field and magnetic field, both of them are basically moving towards the same specific direction or same specific plane, right? And then there are different types of polarization based on the different types of filters or different types of mechanisms doing polarizations. So some examples may be sunglasses or photography or communication channels in different telecommunication technology, right? Where we use polarized light to make sure that we are having a specific light in a specific direction. So this is the idea of polarization. And next we have the concept of non-linearity. So what is non-linearity? This is non-linearity is something which basically arises when the source of the light is really, really strong and the intensity of the incident line is very, very strong. So what happens if you try to force a huge amount of load within a very weak medium, the behavior of the medium is also changed, right? Because of the huge amount of load. The same concept apply in light as well. So when you throw a very intense light over the communication channel or over optical fiber, over a separate medium or different medium, the behavior of the medium is changed at the receiving end because of the intensity, because of the strong intensity of the light or strong presence of the light. So this phenomena is called non-linearity. So different kind of effects can be showed, or different kind of effects can be generated because of this non-linearity. There can be self-phase modulation because of the intensity of the light at the receiving end. It can change its phase. The phase of the source which was actually transmitted and the phase of the received light will be different because of the intensity of the light and because of its effect in the media while it was traversing through the media. It can be cross-phase modulation. It can be four-wave modulation when there are multiple sources of light. So two or more source of light, they can come up with a complete new wavelength or new frequency of light at the receiving end, which actually was not intended to. So that kind of things might happen. So suppose you are doing wavelength division multiplexing, right? You are doing different wavelengths over a same optical fiber. So you would want to receive the same wavelengths at the receiving end as well, right? Whatever you are sending, you would want to receive the same wavelengths at the receiving end as well. But if for the non-linearity effect, if you see that at the receiving end the wavelengths are changed, then your data will be lost because your receiving end is not ready to read the changed wavelength and extract data from that wavelength, right? So this is why we have to make sure that non-linearity doesn't occur in transmission media in optical communication channel. So it basically distort the signal, and it basically somebody is trying to or requesting to record. I will decline the request to record the session because we're recording it on your behalf. If you need the recorded session, you just send an email to training@epinic.net. The training team will facilitate the recording version to you. Thank you. So as I was saying, this non-linearity effect really impacts the communication, optical communication, and we really do not want that to be happening in our communication channels. So we need to make sure that non-linearity doesn't occur in our communication channel. To do that, we basically make sure that the uh, intensity of light is within the range of our expected range, and we are using proper source, and we are using proper medium to facilitate a proper communication channel from source to destination. So that was the concept of non-linearity. Next, we have fiber types. So we have different kinds of fiber available in the market, but in a broader aspect or in a practical aspect, we use two kinds of fiber, single mode and multi-mode. So what is a single mode and what is a multi-mode fiber? Single mode fiber is a fiber where one single light beam is allowed to travel from one place to another within that medium. or within that fiber. This is called single mode fiber. For multi-mode fiber, light travels in multiple paths. That means multiple lights can travel together within multi-mode fiber. Multi-mode fibers are used basically for short-range communication distances, where single-mode fiber basically supports long-range or distance communication between node to node. For multi-mode fiber, we basically use them in data centers or in our equipment racks within one rack to another. For single mode, we basically use them in our long haul communication from one city to another. So this is the major difference between these two fibers. And another concept of using light in DWDM is about amplification. So as time and distance goes by, the signal, the optical signal becomes weak with uh, traveling time and distance over the media, right? So it's, as I said, this is completely similar to the transportation system in our real life. So as your car goes by, the fuel goes down, right? So it is almost the same type of concept for light as well. So as time and distance goes by, so if you send a light from source A to destination B, at the beginning, the strength of the light, and at the end, the strength of the light, they will be different, because during the end moment, it will be very, very weak because it has traveled the distance between A and B. For that purpose, we need to amplify, or we need to re-energize the light particle in the path somewhere in between source and destination. This concept is called amplification. So we can amplify lights in different methods. One of them is EDFA, using EDFA, or erbium doped fiber amplifier. We will discuss about EDFA in details in later slides. But for now, just try to understand that there is a concept of light amplification in WDM, where we make sure that the light has same kind of strength from the beginning towards the end, so that the destination can read the signal and can understand or retrieve the data the signal is carrying within itself. So this is the concept of doing light amplification in X or in WDM. Okay, I might be just kind of. Okay. So as I was discussing, light amplification is another important concept in DWDM, where we actually help the light wave to be energized in between the source and destination. And to do this, we use EDFA, where we use the energized particle to mix with the weak light signal or weak light particles, and excite the light particles with the help of the energized particles, and thus achieve amplification in the strength of the light signal. So as I said, we will discuss in details about EDFA in later slides. But for now, grab the concept of amplification. Okay. Next, we discuss this in short, in our introduction, multiplexing and demultiplexing. So as we know that the optical fiber resources are very limited, and to make efficient use of optical fibers, we need to make sure that we are sending as much data as possible within the same single fiber, and we are using optical fiber efficiently. To do that, we need to make sure that we are doing multiplexing and demultiplexing. So what is multiplexing? Multiplexing means combining different signals into one single signal and pass it through the optical fiber. What is demultiplexing? Demultiplexing is decombining or decoupling the signals from one single signal to different signals, which actually were sent by different sources at the beginning. So the reverse process of multiplexing is called demultiplexing. In DWDM, we use wave division multiplexing. That means, what are we multiplexing? We are multiplexing waves. And what are we demultiplexing? We are demultiplexing waves. So what are we doing? In the source, we are sending multiple wavelengths. We merge with the help of a multiplexer, merge them into one single signal and sent it through one optical fiber. And at the receiving end, there is a demux or the demultiplex module, which read the single signal and which decouple all the different wavelengths from that one single signal and deliver them to different destination wavelengths or different destinations. So this is the idea of doing multiplexing and demultiplexing. So this is the mechanism which basically allows high efficient, high speed, high volume transmission from one point to another. So this is the idea which is basically used in DWDM, right? So these are some basic characteristics or behaviors of light. Now it's time for questions. So please raise your hand if you have any question, if you want to understand or want to discuss anything with me. I don't see any hand. That means all the concepts are clear to everybody, right? Okay, then we will move forward to our next presentation or next topic, which is DWDM overview. So now we understand what is OSI layer. We understand in the OSI layer where does DWDM falls, how DWDM is thought of. It is a composition of lights and different physics or physical phenomena of light. We understand different characteristics or behaviors of light, and we understand how light behaves in different conditions. What are the impacts of lights in different media, how light travels in optical fiber, and how we achieve high efficiency within one single fiber. Now we understand all these things, right? So now it's time to talk about DWDM, or the very basic identity of DWDM, right? Moving forward, as I was saying in previous slides, there are different regions in optical domain. There are regions which we see, there are regions which we do not see. For the for the visible region, we can identify different colors for light. for the invisible region, we basically do not identify or cannot identify different color of lights. So these invisible regions, at the one extreme end, we have ultraviolet ray, and at the other extreme end, we have infrared ray, right? So when we talk about optical communication, we basically talk about the infrared ray region, right? So when we talk about the infrared region, there are specific wavelengths for a specific task, and we use those wavelengths for those tasks only, right? So what are those? So as you can see, there are some bands. We have segregated the infrared segment into some different bands: O band, E band, S band, C band, L band, and U band, right? So different bands have different working principle or different usages for communication or for any other purpose. What we are trying to focus here is the C band and L band. These are the two bands who has the lowest attenuation in the whole optical domain, especially C band, and after that L band. But we wouldn't talk about L band right now because it will be an extended version for DWDM communication. So we will talk about L band in later slides, but for now, we really want to focus on C band, which is in between 1530 to 1565 nanometer. That means these nanometer wavelengths, 1530 to 1565 nanometers, these range of waves are basically, these wavelengths are basically used for communication over DWDM. Why? Because they have the lowest amount of attenuation. What is attenuation? Attenuation is something which makes the signal weak, right? So if we can identify a range of wavelength for which light has the lowest effect of becoming weak, we would like to grab that range to be used for our communication. That is why we use C band, since they have the lowest attenuation characteristics for the whole light range. I can see a hand up. Please go ahead.
Hey, this is Pawan.
Hi,
Um,
Pam.
so, um, so when we say the C band, right, 1530 nanometer to 1565 nanometer, all the vendors or the manufacturing or the OEMs has to get uh, adherence or clearance to use only this specific band,
Yes.
and whether this band is used for the multiplexed signal or it is before before the signal is actually multiplexed, where exactly this band come into play.
Very, very nice question. So it's Pavan, right?
Yeah.
Nice question. So I would like to throw the question to all of you. So when we combine all the wavelengths in the C band, when they are multiplexed and when they're sent through the fiber, what is the wavelength of that multiplexed signal? That is what you have asked, Pavan, right?
Yeah.
Yeah. So any idea or any guess from the attendees? I'd really like to hear your ideas, guys.
I mean, it's my guess that the 1530 is further divided, and those divided signals are actually used to multiplex and then send it as a 1530 signal, something like that. My
Okay.
assumption, I'm not sure.
Okay. Okay. Good try. Anybody else?
I think the whole channels will be sent together. So the final signal will be with all the frequencies.
Yes, exactly. So when we talk about multiplexing, we are not talking about changing the wavelength. We're talking about combining them together. Pavan, you get my point.
Mm-hmm.
If
I
I have 5 strings, 5 loose strings, and you need to send them through a straw. So what will you do? You will combine all those 5 strings together and you will make them one single string. That
right.
doesn't change those 5 strings. Those 5 strings are still there.
Got it.
Then you send that combined string through the straw, and at the other end, you again.
You just untangle it.
Yeah, exactly. That is what happening in DWDM. So actually WDM, not DWDM. In WDM, that is what we do. We just combine the signals into one signal. We do not change the wavelength. We cannot do that. If we do that, then actually the signal is lost, right? So the new combined doesn't have any specific wavelength. They are a composition of all the wavelengths which we send. I
Got
hope
it.
that
So
answered your question.
yeah, one thing just to clarify is
Yeah.
like, so before the signal is even been demuxed, right? I mean multiplexed.
Yeah.
So technically we have to send in the same band. Like let's say we have set a signal strength of 1530 nanometer, right?
Wavelength.
All the client wavelengths are subsets of 1530. It's
Yeah.
not a different wavelength, but it's rather than it's 1530 dot maybe 100, 200, 300, and then everything is sent as a 1530 wavelength.
Yeah.
Is that the correct understanding?
Yeah, that is what you're saying. So
Okay.
yeah, you are correct. The client end is having a 1530 nanometer wavelength, where at the uh, at the WAN side, or at the network side, or NNI we call it, we have a different range, right? Why is that? So when we talk about WDM, we are talking about the WAN side. We are sending signals in long haul from one city to another, from one country to another, right? But when we talk about the client side, they are not colored. They are not colored wavelength. We call them gray wavelength, right?
Okay.
They are only 1530 or 1310 nanometer. So these are the two wavelengths we use to communicate at the client end, right? Maybe for multimode, we can use 850 or 830, something like that. But for the client end, we use gray optics. We do not use colored optics. We call the wavelengths colored wavelengths when we go through the WAN side. You will understand more as the theory progress. You will see, and I will explain all the components in the WAN side, in the client side, all the architecture in later slides. So just bear with me. You'll be able to understand more on these concepts in those
Perfect.
slides.
Thank you, sir.
For now, just keep in mind that when we are talking about client side, we are talking about gray lambda or gray optics, which is 1310 or 1550 or 1530 nanometers, something like that. But when we talk about the WAN side, the WDM side, we're talking about colored optics, colored wavelength, which is the total C band, right?
Got it. Got it. Perfect. Thanks.
I forgot your first question. What was your first question, Pavan?
First question was about the OEMs, what
Yeah.
standard they use. I think that answered me,
Yes.
since we are targeting the
Low
colored band, right? So
Yeah.
technically, all the vendors would be compromise, or whenever they build manufacturers, build the equipments, they would be using the same
Yes.
C-band wave,
Yes.
not the.
This C band is universal, and this C band is maintained by all the vendors. As I said in the beginning, I try to keep this as much generic as possible so that you do not need to worry about vendors. You just need to understand the technology. That's it. So when you purchase DWDM products from any vendor, you need to tell them what kind of device you want from them, and those devices are supposed to use what kind of wavelengths. There are odd band of wavelengths, there are even band of wavelengths, there are total range of wavelengths. So you need to mention which segment you want, and these segments are universal for all the vendors. You can take the odd band OTU cards from Sienna, from Huawei, from Infinera, or from any other DWDM provider. You can you can talk to any other vendor, and if you tell them I need the odd band, it's same for all of them. If you tell them I need the even band, it's all same for them. If you tell them I need the whole C band lambda, it is all same for all of them. Does it answer your question?
Absolutely. Thank you so much.
Thank you, Pavan. Okay, anybody else has any query? No, good to move forward. Okay, so as I was saying, that we are trying to focus on C band only because this has the lowest attenuation. So whenever we send signal using these wavelengths, those signals will be less effective to the fact of attenuation. So what is WDM, wave division multiplexing? Wave division multiplexing is combining the different wavelengths from the source into one single signal, right? So if we try to understand the characteristics of prism, we in our early days we studied prism, and prism was a fun thing to study, because when we did some lab with prism, we saw that when sun ray or white light comes through a prism, we get to see different colors at the other end of the prism. That is the concept. Or that is the fundamental of WDM. In WDM, we use the single mode fiber, and within that single mode fiber, we send one single signal, and that signal is carrying all the input signals all together as a combined signal, and at the output we do demultiplexing, and we get those different wavelengths or different signals from doing the demultiplexing. So this is the whole idea of WDM. As you can see in the diagram, at the input, there are different wavelengths. Like we have colored the wavelengths green or purple or different colors, but keep in mind, these are not visible colors. The waves are colored just to make you understand that they are different colored wavelength. They are different these waves have different wavelengths. So each of them is different from each other, but they are not visible color. Okay, keep in mind. So this is the colored are there only to make you understand that they have different wavelengths. So this is the fundamental understanding, or this is the fundamental concept of WDM, wave division multiplexing. So each of the input pulse or wavelength or wave can carry different service, right? Like one can carry video, one can carry Ethernet packet, one can carry voice packet, one can carry SDH signal, one can carry MPLS signal. So it's whatever the payload is, whatever the data is, it's all being converted into optical signals and wavelengths, and then we send those wavelengths through that single mode fiber from one city to another. And when the when the signal reaches the destination in the another city, they do demultiplexing and then they retrieve the payload from the demultiplex signal. I can see a hand up. Please go ahead, say your name and then go ahead.
Hey, this is Pawan again.
Yeah.
So when we say like wave division, we are talking about wavelength multiplexing, right? I mean, so we have different wavelengths set for different types of service, and that job is done by the DWDM itself, the equipment itself.
Yes. Yes. Understood?
Yeah.
Yeah. Perfect concept so far. So it is not mandatory that only one signal can on only one single service is converted into one signal. So one wavelength can carry all these different services as well. It depends on the granularity at the client end and the WAN end. When I will discuss the architecture in later slides, you will understand it more. But for now, just understand the video or voice or data packet or MP, whatever it is, these are the client payload, and we use this payload as our client end service, and we map those services with our wavelength, and we combine those wavelengths at the source. This combining technique is called multiplexing. We send the combined signal as one single signal through the optical fiber. It reaches the destination. At the destination, the signal is demultiplexed. Different wavelengths is then again sent to different colored cards, and then they're more transformed into client signals, and thus the client services are delivered, right? So this is the whole chain of communication. This is the whole process. This is the whole high level concept of DWDM communication. Does that make sense, guys? Anybody want to participate or anybody has any feedback on it? Because this is a very crucial concept to understand. If you do not understand it, or yes, please go ahead.
Uh, Maybe this is a childish question, but then what is the difference between dense wave and wave DWD, like wave division multiplexing versus DWDM?
Yes, good one. I'm coming to that. Okay.
Sure.
First, we will understand what is CWDM and what is DWDM. So when we talk about WDM, we are picking the C band, right? And within that band, we are taking wavelengths one after another, right? So if we take a look, the whole range is from 1530 to 1565 nanometer, right? This is the whole band. So you can have different wavelengths one after another. You can have, as you can see in this diagram, for CWDM, there is 1550, 1570, or it goes to 1590. But within the C band, we have 1530 to 1565. We are taking bands or wavelengths, and between each two wavelength, we are keeping a 20 nanometer gap, right? This gap is called band gap or guard band. Different terms are used in different locations or different places, but they're all the same. Band guard, band gap, etc. They all means the gap between two wavelengths, between two consecutive wavelengths. So when we maintain a big gap like 20 nanometer between two consecutive wavelengths, we call that technology as CWDM, and it is used for lower cost, lower capacity, and shorter distance, right? And when the gap between two consecutive wavelengths is lower than 0.8 nanometer or 8.8 nanometer, we call them DWDM. So what is WDM? WDM is doing multiplexing or demultiplexing based on wavelength. So what is CWDM and DWDM? So when the wavelengths are taken in such a way that there is a 20 nanometer gap between two consecutive wavelengths, we call it CWDM. CWDM is used for shorter distance, cheaper solution, and lower capacity. When we take wavelengths in such a way that between two consecutive wavelengths, the distance of wavelengths is 0.8 nanometer or less than that, we call it DWDM. DWDM is used for long range, higher efficiency, high capacity, and it is expensive. Okay, so this is the concept of WDM, CWDM, and DWDM. For your reference, I have also put a comparison between CWDM and DWDM in this slide. So this is for your reference only. You can take a look. As you can see, the wavelength range is different. The number of channels supported are different. The channel spacing is different between these two. The cost is significantly different. CWDM is significantly cheaper than DWDM. And also the capacity is same. The capacity is also significantly lower than DWDM. For DWDM, you can achieve a lot more compared to CWDM. So I hope that answers your question, Pavan. I can see one. Yes, please.
Okay, so my question was that like in the previous slide we seen like single mode fiber and we are sending like multiple wavelengths from one end and decoding demuxing at another end, right? So that's a one-way communication.
The one.
So that's that's one. So
Yeah.
it is the one-way communication, right?
Yes.
So for the two-way communication, we'll need another single mode fiber with reverse direction, right?
Fantastic. I would really appreciate this feedback from you. Yes, since we are doing a complete communication in a duplex manner, in DWDM, one-way communication is done over one single fiber and the other way communication is done over the other single fiber. I hope that point you.
Yeah, is it because of the single mode fiber? If we are using, can we use multi-mode fiber to avoid that? Like, no.
Because multi-mode fibers, in multi-mode fibers, multiple signals can travel. That is true, but the wavelengths multi-mode fiber supports are not in the lowest attenuation grid. So can you recall the wavelength which multi-mode fiber supports? It's
So actually, I was just asking the question, like, I'm not sure.
Okay. The answer to your question is no. You cannot use multi-mode fiber for DWDM. The reason to the answer is that for multi-mode fiber, the supported wavelength does not fall into the lowest attenuation band of the wavelength band, right? So what we saw in the wavelength band, the lowest attenuation band is C band, where the multi-mode fiber falls into the 850 nanometer or something like that. So that is why for multi-mode fiber, you cannot use it for long haul communication because signals will be too weak to pass through and you will be needing a lot more number of amplifiers to complete the signal from one source to one destination, and including that much amplifier in the transmission system will also introduce that much noise, which basically distort the signal. In this way, you will not be able to communicate. So you cannot use multi-mode fiber for DWDM long haul transmission. But you can use multi-mode fiber in the client side, in the same data center, or connect with the rack beside your own rack or within your own rack, that is okay. That is why multimode fiber is only feasible for short distance, not long distance. I hope now you understand why, right?
Yes, yes.
Okay,
Thank you.
thank you. I see another hand goes up, please. I think there is two.
Okay. Hi, Jubar bhai.
Hi.
Happy to see you again. Just I have one more question about CWDM. Does it fall in C band
Could you please?
or S band? Yeah. Yeah.
So,
Am I audible?
yeah, please say your name and then your question.
Oh, I'm Tanvir from Dhaka.
Yes.
So I have a question about CWDM. That is, in which band CWDM falls? Is it in S band or C band or L band?
So as you can see, CWDM supports 18 channels in the 1270 to 1610 nanometer range.
Yes.
So this is a wide range of wavelengths. This is a wide range of wavelength range where you have the C band as well. But DWDM only works in the band and L band. It doesn't work in any other band. I hope.
Thank you. That answers my question.
Thank you. Yes, Shekhar.
Yeah, Zubair, so my question is there some preference for usage of LED and laser for say shorter distance we are using laser LED, and for long haul we are using laser, or it's not like that?
No, it's not like that. So for shorter distance or longer distance, you will basically look at the medium which can carry your signal. Your signal might be in any wavelength of in any form, but you need to understand through which medium these wavelengths are passing through, right? Suppose you are sending a very weak light through a swimming pool. So from one point to another, it will not be that much bright towards the end. So if you send one torchlight and if you send 5 torchlight together, definitely you will see that the 5 torchlight are more brighter than the one, right? That is one point. But again, if you use the same scenario, not in water, but in air, you will see that both the lights are visible better than they were in the water, right? So it basically depends on the medium, on the media through which light is traveling, the wavelengths are traveling. So if the media is capable enough to carry the wavelength throughout a long distance and is still at the destination, the strength of the wavelength is intact, then you are all good. So it doesn't basically depend on the source or type of source. It basically depends on the type of media which the light is passing through. I hope that makes your answer.
Yeah. Another question I was having is, DWDM equipment might be using like higher power as compared to CWDM.
Yes,
Because
definitely. Yes, because CWDM equipments are smaller and DWDM equipments have a lot of things in place with multiple amplifiers and multiple lambda conversion from gray to color, color to gray, doing all kind of
कॉल फॉरवर्डिंग आ रहा जी तेरे इसमें कॉल फॉरवर्डिंग आ रहा तेरे इसमें
so yes, DWDM boxes or equipment
ये देख
have much more higher power compared to CWDM.
okay.
ये मेरे ख्याल से गलत दिखा रहेगा सर ना एक्सपायर्ड सितंबर 2024 होना चाहिए
Mute your mic, please.
लेकिन यहाँ पे लिखा है ना PO is expired
Yes. So I think Ranjit, please go ahead. You had your hands up. No. Okay. Mr. Kamal, yes, please go ahead. You are mute, so I cannot hear you, Mr. Kamal.
It's a very effective and informative lecture, Khan sir. So only point I want to know about the DWDM, can we have more than 96 plus channel?
Yes, we can. We can, but in that case, we need to change the band. We need to go from C band to L band. We have those discussions in the later slides because that is a very mature discussion. But to answer in short, to answer your question in short, yes, we can.
Okay.
That involves a lot of arrangement, new addition to your system as well. So that is a whole different scenario and new discussion. But to answer in short, yes, we can.
A silly question, another silly question regarding this. Can we use single fiber for both communication? Matlab, both way communication.
No, we cannot. We cannot use single fiber for both way communication. So as you can see, if we go back to, we had the discussion a couple of minutes ago. So as you can see, from one way to another, we need one single fiber to send all the combined segment wavelengths from source to destination, and we need to do the vice versa mechanism through another fiber.
Yes, sir, can I ask one question?
So we need a pair of fiber to do a complete communication.
Yes, where this is actually I have a question.
Ranjit, yes, please go ahead. Sorry, Ranjit, can you unmute and go ahead? Sorry.
Yeah. So I have only one fiber available between point A and B. So in that condition, can I say, choose WDM or CWDM? What is the equivalent multiplexing available?
I cannot understand your question. Can you repeat?
The thing is actually from point A to B, I have only one fiber available.
One fiber.
It's not actually available, one fiber available. So can I use the WDM or CWDM? What is the equivalent multiplexing available?
So if you have only one fiber available, that is what I was answering to Mr. Kamal. If you have only one fiber available, you are not supposed to do DWDM or CWDM, because DWDM and CWDM are supposed to use two separate single optical fiber to complete the communication in both ways. Now, several vendors can come up with several technologies in their own proprietorship. Their cards may be designed to use one single fiber to do the both. It might happen for CWDM, but I do not see it happening for DWDM by any chance. So I do not have any specifics on these ideas, but as from theory point of view, as I told you from the very beginning, I'm talking a generic way of speaking. As from theoretical knowledge or generic way of speaking, you must not consider CWDM and DWDM over one single fiber. Even the vendor offers you, still you should not, because that will create a whole lot of different kind of complexities in your network. I hope, Ranjit, that answer your question.
Yeah, thanks. Yeah.
Thank you. Kamdi, you had your hand up. Please go ahead. Vaishnavi. I cannot hear you if you're saying something. Yes, Rice, please go ahead. I think Vaishnavi is not there. Rice, please go ahead if you have anything to.
Yeah, yes, yes, sir. Thank you. I would like to continue the Ranjit's question. Is not there any possibility where we can transmit on some frequency and receive on the other frequency in the same fiber, single fiber? Will not that work?
I would say no.
You got my question, sir?
Yes, you're talking about using one single fiber to transmit and receive.
Receive, yeah. To achieve this, to achieve the DWDM.
In both direction doing WDM, right? That is.
Yes, sir. Yes, sir.
Yeah. So
exactly as you discussed, sir, that we require minimum 2 fiber necessarily to
yes,
achieve this. So
yes.
is not there any possibility that on a single fiber, on a single this strip, we do transmission on say ABC frequency and a reception on another frequency?
So to my knowledge, it's not possible. Okay, as far as I know from talking to different vendor, working with different vendor for past 10 to 8 years with DWDM. From my knowledge, I am not aware of something like this for DWDM. That is what I would say.
Thank you, sir. Thank you, sir, for clarifying.
Thank you. Vaishnavi, are you ready to talk now? No. Tanvir, you have your hand raised.
Yes, I have one more question. That is in the comparison sheet between CWDM and DWDM, we are seeing that optical components requires temperature controlled lasers.
Yes.
So my question is, in the countries like where temperature is -5, -7, -10, what happens there? Are they using what kind of heating equipment to achieve the temperature?
That's all?
Yes, for now.
Thanks, Tanvir. Nice questions. Good interaction. I really appreciate, guys. I'm having fun with all of you. So temperature. So whatever the outside temperature is, whatever the temperature you have in your environment for operating any specific DWDM material or boxes, you need to maintain a specific temperature for the shelf. For countries where it is summer based, they use air conditioner. For countries it is cold based or snow based, they use air heater. So that's the difference. You have to maintain a specific humidity for the air in the knock room or in the equipment room. You have to maintain a specific temperature in the equipment room. And also the boxes, the equipments for DWDM, they have a very strong fans, which basically helps to cool down the boxes from being hot or from being high temperature. So what happens when the temperature is outside the range? It might be colder, it might be warmer or hotter. When it is outside the threshold range, the lambdas, the shape of lambdas, they start to change their shape. They start to overlap with each other. As you know, as you can see in the diagram for DWDM or CWDM, they they are sent over different wavelengths, different lambdas, right? And each lambda has a lambda gap between the next one. So between two consecutive wavelength, there is a gap, right? And if the lambdas are changing shapes, that means the gap is changing as well. That means they are overlapping on each other. That means the communication is distorted. So that is why temperature is very much sensitive, especially for DWDM. And as I was saying, Tanvi, to answer your question, for coal-based countries, they use room heaters or warmers to keep the temperature up and in the threshold of the DWDM device. So that is what they do. I hope that answers your question.
Yes, thank you.
Thank you. Yes, Amarjit, please go ahead.
Hello, sir. So can in DWDM can we further reduce this channel spacing to increase the number of channels?
Yes, but we do not increase the channels in that way. Please bear with me. You will be understand these things by the end of tomorrow, I believe.
Right. Okay.
This is too early to explain because we have to go through a lot of primitive fundamentals before that. But to answer your question, yes, the gap can be adjusted and we can increase the number of wavelengths, but in some different way, not changing the gaps.
Right, sir. Thank you.
Thank you. Okay. Anybody has any other questions, guys? I don't see any. So yes, Vaishnavi, I can see your hands up for a long time, but I cannot hear from you. That went down again. Okay. So we have 1 hour left for today. And before moving to the next slide, we would take a short break for 15 minutes and then we will come back. So I'm putting a timer again. So we will be back after 15 minutes. Thank you. Welcome back, everybody. I hope you can see my screen and you can listen to me clearly. Thank you. Thanks. Thanks for confirming that. I was looking in the chat and Vaishnavi, you asked about the band between 1625 and 1675. So if you take a look at the screen, as you can see, the band for 1625 and 1675 nanometer, we call it U band, and it is used for ultra long wavelength. We call it ultra long wavelength band. So in this band, the theoretical loss should be 0.35 dB, 0.3 to 0.35 dB or 0.4 dB, something like that per kilometer. But nowadays, the fibers are made in such a way with advancement of technology that the loss factor for U band is now a bit compensated in modern fibers. So we will talk about fibers later slides, you will see. But for U bands, that should be the loss range or attenuation range per kilometer. And we use this U band for expanding the DWDM wavelengths band. So these ultra long wavelengths are used for very, very expanded DWDM networks. And it is very much costly and very rare. And we also used for a different kind of monitoring functions as well, like long range OTDRs. So this kind of cases we use U band. I hope that answers your question, Vaishnavi. Okay. So Satish, what is the data carrying capacity of each channel out of 96 WDM channel? So the capacity of the channel depends on your network design. You can use 10 gig channel, you can use 100 gig channel, you can use 400 gig channel, and also the type of web you are using, the modulation your wavelengths are using. There are several modulation techniques in digital signal processing. So we know about BPSK or QPSK or QAM, this 8 QAM, 16 QAM, 64 QAM. So these are different modulation techniques. And based on this kind of techniques, the capacity basically depends. Also, it depends on the distance. It depends on the distance you are using your lambda in between source and destination as well. It depends on the loss of the fiber path or the OSNR of the path as well. So to answer your question, I cannot exactly say what is the capacity of each channel out of 96 DWDM channel. It depends on a lot of various things, but you can use each channel to be 10 gig or 100 gig or 400 gig or 600 gig or even 800 gig as well per channel. So it depends on your network topology, on your fiber path, on the modulation technique of your lambda card, on your OSNR of the network, all those things. I hope that answers your question. Anand, Anand is asking, after C and L, which band is being considered for DWD expansion and why? As I said earlier, U band, after C and L, you need to expand to U band, and that's the end of it. Because once you are done using C and L band, the rest of the band is now U band, which you can operate on. But again, that is going to be a very, very costly solution for you and a very rare one. I can hardly I don't think a lot of vendors are gonna propose any solution with U band to U. Yeah, because it will be very much out of scope kind of thing if you have a very uh, moderate or expanded network, even for expanded network as well. Yes, the subsequent question is each channel represents separate lambda is yes, Satish, each channel represent separate lambda. By channel, you mean, I don't know what do you understand by channel, but by channel, I mean the wavelength. Each wavelength means separate lambda. Each wavelength means separate channel. Each wavelength means separate capacity. So if you have 30 wavelengths, 30 channels, each channel will have a specific amount of bandwidth associated with each. So maybe there may be 100 gig channel, there may be 200 gig channel, there may be 400 gig channel, there may be a mixture of different capacities for different channels. But yes, each of channel means each of wavelength, and each of wavelength has its own capacity. I hope that answers your question, Satish. Yeah, okay. So anybody has any other question? No? Okay. Okay, moving forward. So we stopped here, right? Okay. The next one, DWDM. So as I was saying, DWDM, dense wave division multiplexing. So the definition of DWDM lies in its own name. It is doing wave division multiplexing, and the waves are picked in a dense manner, right? So within the C band, as you can see here, the band is shown. Within the C band, the DWDM uses basically from the beginning, it's 1530 to 1560 and onwards for expansion. That's a separate discussion. But for beginning, you'll start C band. I will again request everybody to keep your mics mute so that there is no disturbance for the others. If you have any query, please raise your hand. Thank you. Okay, so as I was saying, each of the wavelength or each of the channel has its own capacity. It can be 400 gig lambda or wavelength. It can be, so for wavelength or channel, we call them lambda in DWDM, right? So it can be 400 gig lambda, it can be 200 gig lambda, it can be 100 gig lambda, it can be 800 gig lambda. And between two consecutive lambda, there might be different types of channel spacing. There might be 50 gigahertz, 100 gigahertz, 200 or 400 gigahertz, right? So this channel spacing also depends on the design of your network. So it can be any one of them. So if we take a look based on different channel spacing, your spectrum, your traffic carrying spectrum will look like this. As you can see, for 200 gig spacing, there is 20 channels in the C band. For 100 gig spacing, there are 40 channels. For 50 gigahertz spacing, there are 80 channels. So for different kind of spacing, different numbers of channels are there. So you can say that, okay, I will increase the number of channels by lowering the spacing between them. For example, I will go with 50 gigahertz spacing and I will use 80 channel in the C band to maximize the capacity in my network. Yes, you can. but for that, you have to design your network accordingly. It is not like that you just plug in your DWDM equipment and it will start running. You have to make sure the path is also ready to carry the load of 80 lambda. So the whole network has to be designed in such a way that all the lambdas, all the 80 lambdas can be carried throughout the whole path from source to destination. So what do I mean by this statement? What I mean by this statement is that you have to make sure you are using proper number of amplifiers, proper number of line amplifications along the path in such a way that all the 80 lambdas are able to maintain the same kind of signal strength from start to end. You have to design your optical fiber accordingly. You have to design your amplifiers accordingly. You have to use and you have to minimize the losses in the path, in the equipment in such a way. You have to use gains and boosters, amplifiers in such a way that all the 80 lambdas can have similar strength from beginning towards end so that the destination can actually read the signal and demultiplex those 80 lambdas. I know that doesn't make a lot of sense right now, but I want you to understand for now that it depends on a lot of various factors. So yes, you can have higher lambdas, but you have to make sure you are providing a very good OSNR to all those lambdas to be carried out from source to destination. I hope you understand this point, right? So moving forward, what are the benefits for using DWDM? So as by now you understand, DWDM system is able to handle a lot more bandwidth compared to any other communication technology available in the market, right? And it is used for long distance transmission. So you can travel from city to city, from country to country even with the help of this technology, right? It is highly scalable. You can start from small and grow to a very high extent based on the traffic requirement in the network. It is also cost efficiency in terms of fiber. If you compare the number of fiber required to carry this much traffic from one point to another to the distance it is being used, DWDM is very much cheaper than implementing fiber because DWDM is using multiplexing and demultiplexing technology in its own inherent property, as its own inherent property. So that means DWDM is capable to get the highest amount of efficient usage of optical fiber. As we saw in the first session, the optical fiber is a very scarce resource in telecommunication industry. DWDM plays a very big vital role to make sure that the optical fiber resource is used with efficiency to transmit high chunk of data in a very high speed from source to destination. So this is how it becomes cost efficient. Also, it supports multiple protocols. So whatever the client end is, it doesn't matter. It converts the client payload into optical domain and then it transmit. We will see those conversion or those overhead things tomorrow. But for now, try to understand that it is there to support a lot of variety of payloads from one point to another. So resilience and redundancy, DWDM can be designed in such a way that you can have zero downtime for very, very long time, unless until some major disaster or natural disaster happens. So if you are having stable network environment, DWDM can give you a very good level of redundancy and a very resilient type of scenario for your SLS as well. You can use dynamic bandwidth allocation feature in DWDM, because when you have a DWDM network in operation, you are basically having a lot of capacity from points to another different points. So it is very easy for you to allocate capacity in a very dynamic way, just like on the go. So DWDM provides that kind of facility as well. It enhances the signal quality. It makes sure that the received signal is error-free in its own mechanism. We call it FEC. So we will discuss those things in later slides, maybe tomorrow or the day after tomorrow. So with the help of its own mechanism, it makes sure that the transmission is error-free, and it tries to compensate whatever the error has happened in the path up to a certain level. So it's very helpful to enhance signal and make sure your data is intact. And also application versatility is there. So you can use DWDM in 4 metro long haul network, in data centers, submarine cable systems. So all those locations or networks which are in need of carrying high chunk of bandwidth over a very long distance with a very short time or with a very great speed, DWDM is there. So these are the benefits of DWDM. I hope till now everybody is with me. So if you guys have any question, I will check the questions for now, and then I will go to the next one. Please raise your hand if you have any query till now. Yes, please.
Sir, actually, just this Jagdish here from Jagdish from. I just want to know that like the interoperability challenges repeatedly gets more in this DWDM when the comes to the benefits of DWDM. So, is there any process way for that? Actually, just want to know that.
Thanks. It's a very regretful reality. We are not there yet. The interoperability. Yes, we can basically do some interoperability. In that case, one vendor's box will be shown as a black box to the other one. And when you do that, none of the vendor will guarantee, or none of the vendor will take stand and stay beside you and make sure that it will work. But in some cases, for some vendors, it works. But the vendors will not guarantee you. The vendors will not ascertain you that it will work.
Oh,
so the reason behind it, what happens when one vendor is transmitting lambda with its own transmit power, that lambda is flowing its own amplifier, own booster, and that lambda is designed to pass through the network only their own equipment from source to destination, right? Once you implement the whole network from one single vendor, that vendor use its planning tool software to plot the whole network, taking the loss, taking the number of nodes, locations, add drops, number of lambda, OSNR of the whole network, put them in the software. The software gave them the value of the fixed data or amplifiers or boosters, gains and everything right? When you put a different vendor's box in the path, that different vendors box have their own characteristics in their own cars. Their insertion loss is different. Their attenuation is different. Their gain is different. So that is where the conflict arises. And that is why no vendor guarantees that their lambda will pass through another vendor's equipment. I hope my point.
Yeah, got you. I got your point. Because multiple lambdas, when we try to carry with other OEMs, we face these challenges repeatedly. So I
Yes.
got you. Got it. Thank you.
Thank you very much. So that's the funda. That is why it is not guaranteed and we are not there yet. But in my experience, I have managed to run Lambda from one vendor within another vendor's network. I have managed to do that. And I have done it with commercial traffic. So yes, it is possible. Okay. Moving forward. So any other question from anybody? No. Okay. So I'm moving forward with my discussion. So we have been discussing some characteristics of lights in our early sessions, right? So we have discussed that light has a few characteristics, light dispersion or polarization or attenuation or non-linearity effects. It's basically involved in the physics of light. This is how light is, right? And I also said DWDM is nothing but a game of light and fiber, right? I will be saying this line again and again throughout the next 2 days as well. So as time goes by and move forward, you will understand how deep this sentence is, how strictly this matches with DWDM technology. So we discussed dispersion. So what is dispersion of light? Dispersion of light means some phenomena or some criteria of light where the shape of the light wave spreads and it gets broadened and it starts overlapping with the next one, right? This is the idea of dispersion. So to be precise, we call them chromatic dispersion. This phenomena of broadening the wave shape and overlapping with the next one, this phenomena is called chromatic dispersion. And then we have polarization mode dispersion. So what is polarization mode dispersion? We know light is an electromagnetic wave that it has a magnetic plane, it has an electric plane, right? So two planes traveling in the same direction, right? So when the light starts traveling, both the planes are in sync. But as time goes by, they becomes out of sync. So as you can see, in the start or in the beginning, they were like this, but over time and distance, maybe one of the webs in one of the plane got weaker and fall behind. So this phenomena is called polarization mode dispersion. So as you can see in the diagram, the chromatic dispersion means, as you can see in the beginning, the shape of the wave was this much, and at the destination the new shape has become like this, extended. This is chromatic dispersion, and this happens because the signal got weak and the amplitude of the signal goes down and both the sides goes spreaded. So this is how it happens. And for PMD or polarization mode dispersion, as you can see, light is traveling in the same direction, for electric and magnetic field, but over time, the two axes or two fields got out of sync with each other, and one of them got lagged behind. So now both the fields are not in sync. They have different velocities in different plane, right? This phenomena is called PMD, polarization mode dispersion. So both these phenomena happens in DWDM. Since in DWDM, light needs to travel over hundreds of kilometers from one point to another. So both of these phenomena happens because of light traveling a very long distance. For DWDM, we need to make sure that these phenomena are taken care of. So what is happening? So in case of chromatic dispersion, as you can see, the wavelengths are like this with appropriate gaps among each other. Between each two consecutive wavelengths, there is a clear gap, right? But because of chromatic dispersion, when it happens, the wavelengths are spreading. The shape of the wavelengths are spreading and they are overlapping with each other. Now there is no clear gap at the bottom with each other, right? They are overlapping with each other. So this is causing interference. One wave is trying to distort another one. So this is the outcome of chromatic dispersion, or we call it CD, right? Which in technical term we call intersymbol interference, or ISI, leads to performance impairments, right? And for chromatic dispersion, there are several ways to maintain that, to make amendment to chromatic dispersions. So one of the major, or one of the significant factor is fiber. So among all the measures which can be taken, one of the significant factor is the fiber. So there are different types of fiber which can be used in different scenarios. And these fibers have different specifics and characteristics. We will discuss about the fibers in later slides. But for now, just grab the idea that using proper fiber, appropriate fiber for appropriate cause can actually take care of chromatic dispersion. So ITU has defined different specifics for different kind of fibers based on their characteristics. So as you can see in the diagram, I have written some specification of fibers like G.652, G.653, or G.655. So there are several kind of fiber which can be used for optical communication, but you have to take into account that you need to use a fiber or a type of fiber which can take care of non-linearity effect, which can take care of low attenuation, which can attenuation effect, which can take care of dispersion effect as well. So there are fibers which are made in such a way that their medium are able to provide a resistance against dispersion. So how is that? So when dispersion happens, like chromatic dispersion happens, when CD occurs, there is a dispersion index for each of the medium. So say, for example, from point A to point B, there is a fiber, and that fiber has a dispersion index of 0.5, for an example, just for an example, 0.5. So if you can add another fiber of the same length, which has a dispersion index of minus 0.5, then altogether the dispersion will become 0 at the end. Does it make sense? So it will be looking like this. So for example, you are sending signal from point A to point B, the red line, and because of the dispersion coefficient, the number is increased in the delay axis, right? And if you add a pool of fiber of same distance from A to B, which has a negative coefficient, same value of this positive one, altogether the dispersion will become again 0 at the destination. So is it understood or not? Guys, I need your response. This is because this is a very crucial concept to understand. Anybody has any question on this? I will discuss more, but for now, anybody has any question on this? If you have, please let me know. Yes, Shail, please.
Clear, like we are adding the same distance of fiber with negative.
Yes.
Will equalize.
Yes, we are adding the same length of fiber, but with negative value of the coefficient. That's it. That's what we are doing. So as you can see in the graph, the red one only has positive value, but the green one has negative and positive both kind of values. Use Kyle, can you mute yourself? I'm getting a lot of background noise from you. I'm requesting everybody to keep your mic mute. So as I was discussing, Shail, let me know if I'm pronouncing your name correct. If not,
Yeah,
I
correct.
apologize. So,
Correct.
so Shail, as you can see in the diagram in this graph, the red fiber, it has the positive index for dispersion, where the green fiber, its coefficient value is a little bit shifted from the positive zone. That means it will have a negative part, also it will have a positive part. Now you can ask, why is this one having a positive part? Why doesn't it has only the negative part to balance the whole effect, right?
Yeah.
Because if we use a fiber which has a complete negative part, then like this one, then what will happen? Non-linearity effect will rise. You get my point?
Okay.
So we have to maintain a balance in such a way and take such a fiber which will take care of non-linearity as well as dispersion. So we take a dispersion shifted fiber. We call this kind of fiber dispersion shifted fiber. So this fiber is used as pool, and the same amount of distance is pooled in the module with negative coefficient in such a way that it minimizes dispersion, and also it doesn't help to bring on the non-linearity effect as well. I hope that answered your question, Shahid.
Yes. Yeah.
Thank you. Next one, I cannot pronounce your name here. Could you please say your name?
Yeah, this is Pavan.
Pavan, yeah.
Sorry for the um
Yes.
misconfusion on the
Yes.
name. Yeah.
It's
So
all good.
basically, the type of fiber that needs to be chosen, this is basically a decision that is made by the dark fiber provider, right? It's not something which I'll be. So if there is a data center 35 kilometers away and I want to connect these two data centers. It's not necessary that I'll lay my own fiber, right? It's basically I'll get some local dark fiber provider, and then just have my DWDM equipment, say A and Z point. So this is something which is taken care by the fiber manufacturers, or the dark fiber vendors, more of, rather than I as a DWDM user to actually consider this, right?
Yes, you are correct, Pawan. But the thing is that when you work with a network provider, transmission provider, like your fiber vendor or fiber provider in your locality, they are likely to consider the fact that they need to provide DWDM services as well to their clients, and they are likely to deploy appropriate fiber in the long haul accordingly. So as you can see, G.652 is the conventional one, which can basically carry DWDM signal. G.655 and G.653, they are also usable fiber for DWDM as well. But for G.652, it is basically most widely common among all the operators based on the cost and attenuation, and based on the universalness of its characteristics. So if you talk to your fiber vendor or transmission provider, and if you ask them what is the ITU standard fiber of your fiber you have provided me in the long haul to carry my DWDM traffic, they are supposed to get back to you on that, and in that way you will be able to know what type of fiber they are using or they are providing to you. I hope that answers your question.
Got it. Yeah. Knowing the underlay fiber standard always helps to identify which
Yes.
possible frequency I can be using on the.
It majorly helps if you own the DWDM and fiber domain yourself altogether. But if you have a dependency, if you can only have the active network, and if you need to take the passive network from somebody else, you need to talk to your vendor of DWDM asking for their preferred fiber standard in the long haul, and you need to convey that message to the transmission provider as well, that you want this kind of fiber specification for your transmission part, or as your fiber in the fiber duct. I hope that
Right.
answers query.
Got it. Yeah. Thank you so much.
Thanks, Pavan. Yes, anybody has? Yes.
Jagdish here, sir. I
Yes,
just want to know that recently, no, these means I have been getting that G.652D something A1, A2, and also coming in the market now. So are
Yes.
these are also the same kind actually, or there are the upgradation versions actually?
So the A, B, C, D are the expansion or modification of the mother one. So G.652 is the mother. And not only 652, you will get different subcategory under a major category. And those subcategory basically different kind of modification or enhancement of different features. Some are sensitive to bending, some are sensitive to splicing, some are there to show good resistance to dispersion, some are there to show strong resistance to non-linearity, some are modified or enhanced to carry ultra band. So you get my point, what am I trying to say, right? So
right.
you need to go through the specification to know about its characteristics, and all these specifications are open free on internet. You just need to know the specification number to find out its characteristics.
Due to these chromatic dispersions, actually repeatedly we will be getting increase of amplifiers, I believe, na, sir, actually as of
For CD, you basically use a lot of interference and distortion. And if you want to if you want to get rid of CD, you need to plan your DCM or dispersion compensation modules accordingly, because there are different classes of dispersion compensation modules. Different classes have different length of fibers, type of fibers, coefficient value of fibers in them. So you have to match those fibers, distances, values, and you have to place them accordingly to minimize the effect of dispersion which occurs before it reaches the dispersion compensation modules. I hope that answers your question. Yeah.
Sure. Got it. Thank you.
Thank you. Anybody else has any query? No. Okay, so moving forward, till now we talked about chromatic dispersion and dispersion compensation fiber. So now we have polarization mode or PMD. So we have already discussed what PMD is. When light moves in such a way that the electric field and magnetic field has different velocity in their own plane and they are out of sync, in that case, this PMD occurs. And PMD is taken care of in DWDM with the help of active equipments. So your transmission equipment in DWDM, which throws the lambda, has the value of its PMD. So it operates within that value and it helps to get rid of PMD itself. So there is nothing major you need to take care of actually. It is designed and proposed by the vendor while they assess your network during the planning phase of your DWDM network. So it is already taken care of at the start of your network. Optical power. So as we are talking about optics, it has to have a measurement to measure its strength, right? So optical power shows the strength of any signal, how weak it is, how strong it is. So it is expressed in milliwatt, and it can be transferred or converted into dBm. So decibel, dBm. So there is a formula in the screen, as you can see. So P dBm is equals to P milliwatt divided by 1 milliwatt 10 log base. That means the logarithm value becomes the dBm of power, optical power. As you can see in the diagram, so P1 is 1 lambda, P2 is another lambda. When they are multiplexed, the total value of lambda is P total, where you can see both the lambdas are there. Few of you are hitting the record button again and again, and I'm declining the request one by one. I'm again requesting you not to record the session. It is already being recorded by us, and you can get the recorded version just to send an email to training@epinik.net. You will get the reply from our training team regarding the recorded version. Moving forward, as I was discussing, so as you can see in the diagram, P1 and P2 separately going from the transmitters, and after multiplexing both the signals, they have become P total. And as you can see in the diagram, in the P total, there are two wavelengths, right? So what is the relation in terms of optical power among these P1, P2, and P total? So the P total dBm will be P single dBm plus 10 log n dB. That means total power of the wavelength will be the single power of single wavelength plus 10 log number of wavelength which are passing through that system. So here in this example, the total power in dBm will be single lambda power that is the power of P1 or P2 plus 10 base log n number of wavelengths. Here we have two wavelengths, P1 and P2. So it will be 10 log 2 dB. So this is the relation between the total power and power of separate lambda in a system. So to summarize the optical power discussion, what is optical power? Optical power is units or measurements of lights which can tell me if the light is strong enough or weak enough to carry or not carry on the transmission, right? So what is the relation? The combined power of the signal is equal to the single wavelength power plus 10 log number of wavelength in that system. So maybe P1 has a value of minus 3 dBm, maybe P2 has a value of minus 3 dBm. So P total will be equals to minus 3 dBm plus 10 log 2, where minus 3 is the power of P1 or P2. They are supposed to be same because we want same level of transmission power for both the lambdas. So they will be minus 3, any one of them. So single wavelength power is minus 3 here in this example, plus 10 base log 2. Here we have only 2 lambda, P1 and P2. So in this example, n will be 2. Now, if you are running a system with 10 lambdas, in that case, the total power of your lambda which are passing from the max unit and which are trying to reach towards the next destination, the total power of that signal is equal to power of single lambda. So for 10 lambda, each lambda has its own power and they are supposed to be same because they are being transmitted from the same hop, from the same similar type of curve, right? So they will have the same power at the source at the beginning. So the single lambda power plus 10 base log 10, that will be the total power for the multiplex signal. You have to make sure that. So I know it's not completely comprehensive right now. I would like you to request to grab the theory or formula for now, because on day 2, I mean tomorrow, we will do some calculation of optical power in a complete system. And after doing that, you will be getting a clear scenario of calculating optical power in a DWDM system. So you can ask me, so when we run a DWDM system, do we need to do the math on paper every time we do any kind of troubleshooting? Or if fiber card happens, if the re-splice the card and new losses added, do I need to do the math each and every time with pen and paper? The answer is no, you don't have to. Because at the beginning, when the system was placed or installed or designed, actually, it was designed by your vendor in the software, and the software took care of this. And whatever the fiber loss you have right now, the software added a 3 or 4 dB margin to it and then calculated the required power for the amplifier or booster, which need to be set at the beginning. So your system has enough scope to be scalable in case of change in the loss in the path, but the loss has to be within the threshold. If it crosses the threshold of the system will not be able to compensate it anymore. So to answer the question that if you do need to do the math all the time, no, you do not. Your system does it on its own, and it has the capability, and the capability was made sure during the planning stage by the vendor in a software. So it's all taken care of. But you have to make sure your fiber quality or the total loss in each span is similar to what you started with, right? So when you're going to deploy a DWDM network, you have to talk to your vendor and you have to know what is the margin they have kept in the design phase for each path so that you have a threshold at your own hand when you are operating the network yourself. For example, some road expansion work has started in some region. So fibers in that region, underground fibers in that region will get cut every day. And if you do a splice on one specific fiber every day, the total loss of that fiber will rise. So you need to know what is the margin you have in your hand and up to which value you can tolerate the loss. And if you see that the value is crossing, you need to look for alternative path or deploy alternative fiber as soon as possible. So that's the significance of understanding optical power. You do not have to do the math. Your system will do it for you, but you have to understand the consequence and the concept to operate it so that your lambdas do not fail and your traffic do not face any kind of outage. So it is 5:35 right now, and on that note, I will stop here today. We'll start from next slide, OSNR, tomorrow at the same time tomorrow. So before I shut down today's session, I would like to request if anybody has any query on the topics or on the concepts we have discussed so far. Please raise your hand and you are welcome to provide feedback. If there is any question in the chat, let me check. Some vendors, so one of the question from okay, I'm going back to the chat later. Francis, you wanted to say something? No, Rice, you wanted to say something. Yes, Rice, please.
Yes, sir. Shall we get these slides, this presentation?
Yes.
Copy. I mean, a soft copy of the same.
No, you are not gonna get the presentation file. You're gonna get the PDF files, and those files are already published in the course material page in the Epinic Academy. So you're most welcome to have them here, only in PDF format, not in PPT or PPTX.
Thank you. Thank you.
Yes. So anybody else has any question? No. Okay, I'm taking a look at the chat box. Okay, Anand is saying some vendors have even gone with extended C-band since C-band is limited up to a frequency range. How do they find additional spectrum for extended C-band? So the extended C-band is a fancy name for using L-band. So what happens when you use C-band, you are using all the wavelengths in the C-band with 50 gigahertz or with 100 gigahertz band gap, right? So for some vendors, they actually push that limit a bit far and they come up with some more wavelengths, which they call extended C-band, and then they go to L-band. So this is basically pushing your limit in the SIP and nothing else. We will discuss it in detailed manner in upcoming slide. It is too early to talk about this right now, but we have a separate slide on this only. So we will discuss it tomorrow. I hope that answered your question, Anand. Tanvir, you have raised your hand, please. Tanvir, did you wanted to ask anything? I can't hear you. I can't hear you. Okay, I'm going back to the chat box again. DCM modules being used to compensate dispersion along the fiber, does it have the same fiber length coil width? Yes, it has the same fiber length. Not, if not same, close to similar. So if you have a 50 kilo distance between point A to point B and point A, they both will have a DCM which has a 50 kilo fiber pool. Only the core pulled in a module inside them. It will be a 1U pizza box or 2U pizza box. It will be placed beneath the shelf of your DWDM chassis or DWDM shelf. So you will see fiber connecting from your DCM to your DWDM box and vice versa. So yeah. Another question from Anand, what type of fibers are used in DCM modules? Is it G.653 DSF? Anand, I will discuss more on this tomorrow, but it depends. Different kind of fibers are there. There is dispersion shifted fiber. There is non-zero dispersion shifted fiber. So if you use dispersion shifted fiber, that has some limitation that can introduce some effects of non-linearity in the network. So in that case, we use a non-zero dispersion shifted fiber or something like that. So I will discuss in detail in tomorrow's slide when it is appropriate time. So for now, just bear with me. Bala, you wanted to know, we can get PPT? No, you cannot actually. I'm really sorry for that. What do you mean by channel? Channel, by the word channel, I means wavelength, I means lambda, I mean, yeah, wavelength, yeah. So each wavelength has its own capacity, as I discussed earlier. How many terabyte per second in DWDM support? It based on your lambda capacity, your system design, your infrastructure, your fiber loss, your OSNR quality, your lambda modulation, and all that. So there is no specific answer to that. You can have 10 gigs of lambda per lambda. You can have 100 gig per lambda, and so on. Would you mind summarize the today's class? Not actually. I would love to do that. Once I finish the question, Tanmoy, I will try to summarize today's class. Okay, Rajkumar, I hope I have answered you already. Pavan, see you all tomorrow. Yes, apart from C band, what the use of other band? So if you go to the slide, I have provided the usage of other slides, other bands in the slide. Some of the bands are used for PON, passive optic networks like GPON or GPON. Some of the bands are used for ultra high capacity long haul links. Some of the bands are used for DWDM or CWDM. So yeah, I have provided all the details of different bands being used for. Please look into the slide. What could be the maximum capacity from point A to B in 50 gigahertz band gap? So for 50 gigahertz band gap, is it 80 channel or into 800 gig of capacity? So Tanvir, when we talk about 800 gig capacity lambda, the lambda has to be broad enough to carry that much of capacity. To answer your question, the lambda has to follow a specific modulation technique like 16 QAM or 8 QAM or 64 QAM to carry high capacity of traffic. If a lambda follows that kind of modulation, the shape of lambda becomes a bit wide. And when it is wide, it will basically kill several lambda shape or space by itself. But the space between this lambda and the next lambda can be 50, can be 100, can be anything, right? But since the lambda is broadened, it has occupied multiple lambda itself. That means you cannot put the next lambda as your next capacity channel. So in this way, when you are going towards high capacity, the number of lambda will be decreased automatically. We will have a detailed discussion in later slides, as I said, tomorrow, because tomorrow and the day after tomorrow, and in the beginning, because tomorrow we are going to talk extensively about DWDM architecture, lambda behavior, modulation technique, DWDM system design, planning, different technology it uses. So you will be able to get a detailed view on these advanced query, I would say, in tomorrow and day after tomorrow's class. But for now, to answer your question in simple manner, the math is not as simple as that. 80 channel into 100 Gbps. Again, it depends on a lot of things, but most of all, it depends on the architecture of your system and the fiber path or fiber health of your network. So for now, that is what I'm gonna answer. Tomorrow and the day after tomorrow, I will discuss these things in detail with appropriate time. Okay, how many TBPS in DWDM support GBPS, or how many kilometers support? Same answer. It depends on your architecture. You will get a clear view after tomorrow. How many terabyte are support in DWDM? DWDM lambda can carry 100 gigs, 200 gigs, 400 gigs, multiple 100 gigs per lambda. So it depends. What is max wavelength SFP in a DWDM? Available in market, distance at SFP. I'm not sure what do you mean by max wavelength SFP, Bala. If you mean the wavelength of maximum wavelength SFP, if you wanted to mean this by maximum wavelength SFP, so the distance which cover from one point to another is dependent on the number of amplifier booster you are using in your system design. So it depends how much further your lambda can go based on the design of your system. So maybe one of your lambda can go 600 kilometer. So maybe one of your lambda can go only 200 kilometer in specific path. So it depends on the design of your DWDM system, and it is directly related to how many amplifiers and boosters you're using. And also you cannot put number of boosters or amplifiers as per your wish to extend a lambda. your lambda card has to support it. Your modulation technique has to support it as well, because the lambda which is using QPSK and the lambda which is using BPSK and the lambda which is using 64 QAM modulation or 16 QAM modulation, all these lambdas, they have different range to support in terms of distance. So it depends on the modulation technique and your architecture of the DWDM system or design of the DWDM system you are implementing. So it's not based on the SFP. The one and only thing which is dependent on the SFP is OSC, optical supervisory channel, from one node to another. It is between two consecutive node. It is between two consecutive node, and it is a dedicated channel used by the nodes to exchange their command and control and management signals with one another. So the only limitation in distance in SAP is with the OSC for DWDM. So you need to have higher range SFP in as your optical supervisory channel SFP to uh, go to a very high distance, like about 120 kilometer or 150 kilometer or something like that. So I hope that answered your question, Bala. What is the relation between gigahertz spacing and channel? So the channels are wavelengths we are talking about. I'm still sharing, right? Okay. So, so as you can see, these are the wavelengths. So wavelength is the distance between two consecutive waves, their peaks, the distance between their peaks. So these are the wavelengths, as you can see, and the frequency is what is the time it is required to complete one complete cycle for the wave. So that is the difference between frequency and wavelength. It is a vice versa relation, I believe. Why we use DWDM, I have discussed this in my slide, the benefits of DWDM. We use DWDM for high capacity, high efficiency, high speed, achieve long distance transmission, resiliency, dynamic bandwidth allocation, and all those things. So please review the slide again. Transfer distance, I'm not sure what you are trying to say, Bala. You might want to clarify this. Okay. If anybody has any other query, please raise your hand. If not, then I will summarize today's session. So today we went through a couple of slides. First one, we went through our agenda. In the agenda, we discussed what are we going to do, who am I? And we discussed what are the timings there would be. We discussed about apricot coming. We shared we shared our acknowledgement for this content. We shared asking your consent for sharing photography. We shared about our request not to record the session. And then we went to the introduction slide here. We tried to understand where DWDM technology falls into the OSI layer and why. We try to understand what a network is and what types of network we are having. So in which kind of network DWDM falls, we try to understand the requirement of IP traffic, growth of IP traffic, and growth of fiber deployment. So we try to understand there is a gap in between them. What is the way of what is the way out of this gap? We try to understand multiplexing is the way out. Then we try to discuss some properties of light. the physical properties of light, like reflection, refraction, total internal refraction. We try to understand uh, um, different phenomena of light, like attenuation, dispersion, polarization, nonlinearity, and we try to understand difference between max multiplex and demultiplex process. So then we started our next session, DWDM overview. Here we just started discussing what DWDM is, what are the advantages, what is the difference between DWDM and CWDM, and how they both are included in WDM technology, what are the wavelength bands used by DWDM. We try to understand how DWDM wavelengths or band looks like. We try to discuss chromatic dispersion, we try to discuss polarization mode dispersion, and we try to discuss dispersion compensation module. These are the brief discussion we had, and we also had this short discussion on optical power. So in later slides tomorrow, we will have detailed discussion on dispersion compensation module. We will have detailed discussion on OSC. We will have detailed discussion on optical power calculation and so on. So a lot to discuss and a lot to catch up. So that is the summary of our today's discussion. What is optical budgeting while link design? I will get back to this question tomorrow because we have optical budgeting discussion tomorrow. So to answer in short your question, optical budgeting is actually planning for optical loss in your system to keep the threshold in place and design the system accordingly. That is the short answer. We will discuss it tomorrow in detail with exercise. I hope that will clarify. So it's about 6. Thank you guys for staying with me for 34 minutes. We will start same time tomorrow. And thank you for being here with me. So I really appreciate you guys getting engaged with me and interacting with me during the discussion. Keep doing that. It will encourage me more to explain things with my own example and experience. So thank you very much. And see you tomorrow. Thank you. I will now stop the sharing and I'll now stop the recording as well.